Ever wondered how radial basis function networks work? Well, let's unravel this fascinating area of artificial intelligence, radial basis function. Networks, or RBFNs, are a type of artificial neural network used for a variety of tasks, from pattern recognition to function approximation. They shine especially bright when dealing with nonlinear relationships between input and output data, where traditional linear models might stumble. In an RBFN, the network is composed of three main layers: the input layer, the hidden layer, and the output layer. The input layer receives the input data, which is then passed through the hidden layer. The hidden layer consists of a set of radial basis functions, which are responsible for transforming the input data into a higher dimensional feature space. Each radial basis function is centered at a specific point in the input space and has a certain width. The output layer takes the transformed data from the hidden layer and produces the final output. The output can be a single value or a vector, depending on the task at hand. To train an RBFN, we need to determine the optimal values for the centers and widths of the radial basis functions. This is typically done using a process called clustering, where the input data is partitioned into groups based on their similarity. Once the centers and widths are determined, the RBFN can be used to make predictions on new, unseen data. Overall, RBFNs are a powerful tool in the field of machine learning, particularly when dealing with nonlinear relationships. Their ability to capture complex patterns and make accurate predictions makes them a valuable asset in various domains. Whether it's recognizing handwritten digits or predicting stock prices, RBFNs have proven to be effective in a wide range of applications. So the next time you encounter a problem that requires modeling nonlinear relationships, consider using a radial basis function network. You might just be surprised by the results. At the heart of RBFNs are neurons with radial basis functions. RBFNs are composed of three layers: an input layer, a hidden layer, and an output layer. Now, what sets RBFNs apart is the activation function used in the hidden layer. Instead of the typical sigmoid or ReLU activation functions, RBFNs utilize radial basis functions. Radial basis functions, or RBFs, are mathematical functions that depend on the distance between the input data and a center point. When the input data is close to this center point, the output of an RBF neuron peaks, decreasing as the distance from the center expands. This unique property of RBFs makes them excellent at capturing complex and nonlinear relationships between inputs and outputs. A commonly used radial basis function is the Gaussian function. The hidden layer in an RBFN houses multiple neurons, each associated with a specific center point. These centers function as prototypes or representatives of certain data patterns. Every hidden neuron computes its output based on the radial basis function, measuring the similarity between the input data and the center. The number and positions of these centers can greatly influence the network's performance and are often determined through training. The output layer is responsible for producing the final output of the RBFN. It takes the outputs from the hidden layer neurons and combines them linearly. This combination is achieved by multiplying each hidden neuron's output by its associated weight and summing them up. The resulting sum is then passed through an activation function to produce the final output. B-roll change. The weights between the hidden and output neurons play a crucial role in determining the RBFN's performance. During training, these weights are adjusted using a learning algorithm. The goal is to minimize the difference between the RBFN's output and the desired output for a given input. This process is typically done iteratively, with the weights being updated after each iteration. B-roll change. The learning algorithm used to adjust the weights can vary depending on the specific problem and the desired performance. Some common algorithms include gradient descent, backpropagation, and evolutionary algorithms. These algorithms aim to find the optimal set of weights that minimize the error between the RBFN's output and the desired output. B-roll change. Once the weights have been adjusted, the RBFN is ready to make predictions on new, unseen data. The input is passed through the network, and the output layer produces the final result. This result can be used for various applications, such as classification, regression, or pattern recognition. B-roll change. In summary, The output layer of the RBFN combines the outputs from the hidden layer neurons using weights. These weights are adjusted during training to learn the relationships between the input and output data. The resulting output is then used for making predictions on new data. Training RBFNs requires determining the optimal positions of the centers and the weights of the connections. Common training techniques include clustering methods, such as k-means, to identify center locations, and methods like least squares regression to adjust the weights. RBFNs find their use in a variety of applications, including function approximation, time series prediction, classification, and control tasks. They are particularly useful when dealing with problems where the relationship between inputs and outputs is highly nonlinear and may not be well approximated by simpler models. So, in essence, Radial Basis Function Networks, or RBFNs, are a type of neural network that uses radial basis functions in its hidden layer to capture complex and nonlinear relationships between input and output data. They offer a valuable tool in pattern recognition and function approximation tasks, particularly in scenarios where traditional linear models or other neural network architectures may not perform well. So next time you're faced with a complex nonlinear problem, remember RBFNs might be the solution you're seeking.